Okay, sir.
I mean, I've done this in the lecture that I've posted, but since you're the only person here, so I let's just do it again. So you're going to do how to derive from the Schrodinger equation to the Feynman path integral. So now the Schrodinger equation implies as its solution that the time evolution of a wave function, say from given some initial time at t0, is given by e to the power minus I by h bar, the Hamiltonian t minus t naught of psi of t naught. Okay. Welcome, Nahi.
Oh, hello, sir.
Welcome, Isa. So since only Shudak was here at 5 o'clock, I started the lecture, and I'm redoing some stuff because he was absent in the last class. So I'm redoing the derivation of how to derive the path integral from Schrödinger's equation. Okay, I hope you don't mind.
It's okay, sir.
Okay. All right. So Schrödinger equation implies this, right? This is something we all know. This is the formal solution to the this is a solution to the Schrödinger equation. It only holds when h is time independent. Okay. If h has an explicit time dependence, then the solution to Schrödinger's equation is much more complicated. And if you have time, we will do that in time-dependent perturbation theory. Okay. Having done that, so this operator is called the time evolution operator, ut minus t naught e minus I h bar h t minus t naught. This is the time evolution operator. And what it has is that it contains in it all the information you need to know how the system evolves in time. And the propagator, so this thing is also known as a propagator, but I like to call the propagator the position representation of the Schrödinger time evolution operator. So if I take some final position xn and sandwich it between tn and t1, sorry, I'm switching notation now, x1, this is what I would call a propagator. They have the same information as the other one. This has the same information as this one. And we call this something like k, xn, tn, x1, t1. Okay. Now you asked a very good question last time, and it can be written, this thing can be written in the Heisenberg picture as xn tn, x1 t1, where is the Heisenberg picture xt, the state means that it's the eigenstate of the time-dependent position operator at time t, whose eigenvalue is given by x. I'm not saying that t is the evolution parameter of the state itself, because in the Heisenberg picture, the states are time independent. So this is a propagator. Now, what we want to do is that we want to take tn minus t1 to be a finite time interval, but then we divide this time interval by a large integer, positive integer, n minus 1.
Sir, I had a question. So
Yeah.
You just wrote this eigenvalue equation. So the operator x is time dependent. So does
Yeah.
the eigenvalues also has to be time dependent in this
Uh,
case?
yes, I think so. Yeah. Yeah.
Oh, okay.
Yeah. Exactly. Yeah. So, so now this is, we divide the time into, n-1 bits, and each small bit of time interval we call delta t. So delta t is small, okay? So n is large, and delta t is very small. So, so what we have done is that we have taken, this is the time axis, and this is, say, the time tn, and this is, say, time t1, and we have divided up this interval into n-1 pieces, right? And the x-axis is the position axis. So this is at x1, and this is xn, okay? So now what we're going to do is that, we have divided the time in small bits and pieces. So what we are going to do is that we're going to take a propagator and insert a complete set of states at all this intermediate time. Okay? So, for this derivation, I work with, in the Schrodinger picture, I work with this. So we can say k xn tn x1 t1 is x of n u t minus t tn minus t1 x1. And then what we first do is that okay, okay, we write it in the Heisenberg picture first, and you will see why. Because we want to so let's just first say dxn minus 1. So we are what we are doing is that we are inserting a complete set of state here. Okay, and then what we're going to do is that we are going to introduce another complete set of state n minus 2 after this guy. So this should be minus 2, right? Okay, and then we keep on doing this until we get to x2, which is this thing at time t2, right? So at all these times, we are integrating over all of this. So we have an integral over x2, we have an integral over x3, dot, 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 dot. Okay? So here we have x2, t2, x2, t2, but now we have x1, t1 here. So we can rewrite this as the integral over dxn minus 1, dxn minus 2, dx this, and then we have x of n Tn, x of n minus 1 Tn minus 1, x of n minus 1 Tn minus 1, x of n minus 2 Tn minus 2, dot, 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 x2 T2, x1 T1. Okay? Is this clear?
Yes, sir.
Okay. So let's take one of these guys, okay? Doesn't matter which one. Let's call it x small n Tn, x small n minus 1 Tn minus 1. So now let's write it in the Schrodinger picture. Then what we have here is that u of delta t acting on xn minus 1 xn, right? But delta t is very small. Since delta t is very small, we can just approximate it as xn, the bra of xn, the identity operator minus I by h bar, h of delta t. Because u is an exponential, the form of u is and when this is small, we can just keep the leading term in the power series, the leading in delta t. Okay, so is this clear what I'm done here?
Yes, sir.
Good. So and then now we do some gymnastics. We start doing some gymnastics. So the first term is nothing but xn minus 1, and we know that that is normalization. It gives me xn minus delta of xn minus delta xn minus 1, right? This is the Dirac delta function. But we know that from quantum 1 plus and previous courses that this is nothing but 2 pi h bar integral over dp e I p xn minus xn minus 1 by h bar, right? Is this clear?
Yes, sir.
Yeah. So, we can even derive it if you wanted to. To derive it, what we have to do is that we have to insert, what am I doing? We have to insert momentum eigenstate, say dp. And this is nothing but, sorry, not that one. This is nothing but the wave function psi of p xn, right? Where this is the momentum eigenstate. And this is nothing but the complex conjugate of psi of p x m n minus 1. So this should be a tiny bit, should be n minus 1, right? And this we know to be exponential, and therefore we can write it as this, okay?